Howdy folks, how we doing today? In this section, we are going to focus on similar figures. So in 8.1, we looked at the term dilation, which means to take a shape, a polygon, and make it bigger or smaller by some scale factor. Now, why we did that is I wanted to introduce to you guys the whole properties of similar figures, because what it means for two objects to be similar is that they have the same shape, but they are different in size, meaning they are going to look identical to each other, just one is going to be larger than the other. And this is where the whole idea of a dilation comes into play, because we talked about with a dilation that we are making something bigger or smaller by a certain factor. That is called a scale factor. So for example, here we can see that I have A, B, C, D, and I have OLMP, that I can see that this, obviously the second shape is bigger than the other one. They have the same shape to it, but one's bigger. So we can say that there's some scale factor that we're multiplying by to find that. Now, relating this to the actual specifics, this is what you guys had to do in the simulation. When we look at similar figures, what does it mean for them to be the same shape but different sizes? So when we talk about shape, okay, same shape is referring to the angles. What gives a polygon shape are the angles within it. Okay, so within any sort of similar polygons, the angles, the corresponding angles, I should say, are always going to be equal to each other. What I mean by that is, for example, let's say that I have angle C, which is the bottom left-hand corner of that shape. That would correspond to angle O, which is right here. And what you guys discover is that those two angles are going to be equal. I can look at any of these, like for example, B and M, that those two angles are going to be equal. That what it means for two things to have the same shape is that they have the same angles. But different size means the length of the side. So for example, if I look at C to A, which would relate to O to L, that those are obviously different in length. And that's where that scale factor comes in. This scale factor does not affect the angles, but instead the scale factor only affects the lengths of the sides. So if my scale factor was 2, that means O to L would be twice as long as C to A. All right, so we're looking at the same angles but different side lengths. So what it means for things to be similar is that they're going to have the same shape, which means the angles are going to be the same, but different sizes, which means the side lengths are not going to be equal, but they are going to be proportional to each other by a scale factor. Now, how are you going to figure this out? What we're going to have to do in order to analyze these types of problems is we're going to have to figure out which parts match up. To figure that out, we're going to look for what are called corresponding parts. Corresponding are exactly what I said. They are the parts that match up to each other. So they are the matching sides and angles from one polygon to the other. So for example, if I were to look at angle B, okay, angle B being the top of that triangle, I know just by the look of this that this is going to correspond to angle E. And same thing with side length. Let's say I have B to C. Well, that's going to correspond to E to F. Okay, so the angles and sides, we're going to try and match up what things are corresponding. Now, it's nice and easy in this diagram because those two shapes are kind of the same orientation. They're both upright. So what if they're not? What if the one's kind of sideways? How do we figure this out? So one way you're going to see this written is what's called a similarity statement. You're going to look at the two triangles ABC and DEF, and in between them you're going to see this little squiggly line called a tilde. Okay, what that means, that symbol is going to represent similar to. So I would say here that triangle ABC is similar to triangle DEF. Now, why this similarity statement is important is because this is written in a specific order. It is written in a way that the corresponding parts match up. Here's what I mean. Notice I circled angle B. Well, angle B is the middle letter in triangle ABC, and that corresponds to angle E, which is the middle letter here. So my corresponding angles all match up. A corresponds to D, and notice those are both written first. B corresponds to E, like I pointed out, and C corresponds to F, which those are written last. It also is used to show the sides. So for example, I highlighted B to C. So notice B to C would be the second and third letter. That corresponds to E to F, which is also the second and the third letter. So we can look at the specific letters themselves, which are going to tell me which angles correspond to each other, as well as any two letters, which are going to tell me which sides correspond to each other. So a similarity statement is how we're going to, or what we're going to use to try and match up those corresponding parts. All right, so in this first example, we're going to give you two triangles, RST and XYZ, and our goal is to list all the corresponding angles and corresponding sides based upon this similarity statement, okay? So again, looking at the angles, we're going to look at the individual letters, okay? So the letters, we have R, S, and T, and X, Y, and Z. So based on this, here's what I know. I know angle R is my first letter of the first triangle. That's going to correspond to angle X, which is the first letter of my second triangle from that statement. I could say angle S is going to correspond to angle Y, which are the two middle letters. And then lastly, angle T is going to correspond to angle Z, which are the last letters. And again, here's what I know about these is that R and X, again, these are going to be equal. I know that S and Y are going to be equal. And lastly, I know that T and Z are going to be equal. Each of those sets of corresponding angles are always going to be equal because that is what gives something the same shape. Now, in terms of the sides, okay, I have RST and XYZ. So if I look at the sides, and you can use the picture, but let's say I start off with my statement, R to S. R to S would be this bottom side here. So I know that R to S is going to correspond to the bottom side of this triangle, X to Y. And notice X to Y are my first two letters. So I have R to S, which corresponds to X to Y. I can follow my similarity statement. Instead of R and S, I can look at S and T. So S and T would be the second and third letter, would correspond to YZ. Notice YZ would be the second and third. If I look at those sides, here's ST corresponds to YZ. So notice how that matches up. And then lastly, notice I did the first and the second and the third. So the last combination would be the first and the third. So R to T, which would correspond to X to, whoopsie daisies, X to Z. And that would be my last side here, R to T, X to Z. So when I wrote those corresponding angles and sides, again, the angles are always going to be equal, but as we saw that the corresponding sides are not equal to each other. That is obvious here that triangle RST is larger than triangle XYZ. So in this case, in terms of the sides, since one of the triangles is larger than the other, that means that there is a scale factor between them, that the scale factor represents how many times bigger that larger triangle is compared to the second one. So let's say, and this kind of goes back to last section, that I want to find how many times bigger is RST compared to XYZ. Obviously, they're the same shape, but they're different in sizes. So in order to find a scale factor, what we're going to use is our corresponding parts. So using that similarity statement, I just listed off a whole bunch of corresponding parts. If I want to find the scale factor, however, what I'm going to do is I'm going to look at the sides. So I'm going to choose a pair of corresponding sides. So using my similarity statement, let's say that I want to compare R to S and X to Y. I know that R to S from my diagram is equal to 20. I know that X to Y from my diagram is going to be 12. So if I want to find the scale factor, what I'm going to do is I'm going to divide those two out. When I divide them, I'm always going to do this. I'm going to always compare the big to the small, okay? When we did in section 8.1, we looked at the image compared to the original object. Here I'm going to do it big to small, and that's always going to give me a value larger than 1 for my scale factor. So here I would take RS, and I'm going to divide it by XY. So using my numbers, that'd be 20 divided by 12. And if I take 20 divided by 12, I'm going to get a scale factor of about, I'll write this as K, about 1.7. It's rounded. It's 1.6 repeating, but I'll get about 1.7. That is how many times bigger RST is compared to XYZ. So finding that scale factor is very similar to what we did last section with our dilations. All right, so now comparing similar objects, again, we're looking at the same shape, different sides. So it's easy to understand the same shape. We know that the angles are always going to be equal to each other. But what we're going to use this idea of similarity is to find some unknowns. So what we're going to do to find unknowns is we're going to write what's called a proportion. All right, so proportion is going to be a way in which we can take similarity. So obviously when we find similar objects, that they're similar by some scale factor, that one object is going to be bigger than the other. To find that scale factor, what we're going to do is we're going to look at the big versus the small, okay, what I just talked about in the previous example. Now, what we do is we're going to set this up by writing what's called a ratio. This right here is what's called a ratio. Ratio is just a comparison of two sides, okay? Now, if I compare the corresponding sides, like for example, in the previous example, we did R to S compared to X to Y, right? And what I got was 20, whoopsie daisies, I got 20 over 12, which gave me a scale factor of about 1.7. Now, I want to notice that a proportion is what happens when I look at two ratios that are always going to be equal. So what I want to do is, let's say I compared the other corresponding parts. Like, for example, R to T. R to T corresponds with X to Z. Okay, so X to Z, if I were to compare those, what I would have is 25 divided by 15. And if I divide those two things out, what I'm going to get is a scale factor again of about 1.7. And notice that this ratio of 25 to 15 is the exact same result as the ratio of 20 to 12. And I could do the same thing for my last side. Let's say I look at S to T and compare that to Y to Z. Well, S to T I know is 30, and if I compare that to 18, by dividing those out, I'm going to get 1.7. And this is what a proportion is going to relate. A proportion occurs when two ratios are identical. Now, the way I'm going to write a proportion is I'm going to take two ratios. Like, for example, my first two. Say I take RS and XY and RT and XE. If I know that they give me the same result, what I can write is this, is that the ratio of RS to XY equals the ratio of RT to XZ, okay? This is right here is what's called a proportion. Now, why I bring this up is because in order to solve some of the problems we're going to do next, we're going to write a proportion to solve them. So, let's say that I give you two triangles, DEF and MNP. Okay, using my similarity statement, again, I can figure out which are my corresponding parts. What I'm going to do is I'm going to use a proportion to find x. So x is the side length of E to F. Okay, so our goal is to solve for x. What we're going to do is we're going to write a proportion using corresponding parts. So what I need to identify first is, using my similarity statement, is I'm going to identify what are corresponding parts. Now, I obviously want to find EF. So the first thing I'm going to do is figure out, okay, what does EF correspond to? Well, EF, based on this here, EF are my second two letters. That would correspond to NP, okay? What I'm going to do is I'm going to relate that to another set of corresponding parts. So let's say I use DE and MN. So I know that DE would compare to MN. What I'm going to do is I'm going to set up a proportion. There's multiple ways to do this, but here's what I'm going to set up. I know that the ratio of these two sides should always equal the ratio of these two sides. And that ratio is always going to be equal to that scale factor. So what I'm going to set up is this. I know right first that this bottom triangle is obviously larger than the top triangle. So I'm going to set up NP first. I'm going to go NP over EF is going to equal MN over DE. Now, why did I set it up this way? Is because on top, both of this represents the big and the big versus the small and the small. And that is how we always want to find our scale factor. So what I want to do then is plug in my numbers. So I know that NP, for example, is 30, compared to EF, which is X. Again, it's X because I don't know what it is. I know that M to N is 18, and I'm going to compare that to its corresponding part, D to E, which is 15. Okay? So right here, what I wrote, this is what's called a proportion. Now, what we're going to do is we're going to try and solve this, and our goal is to solve for X. So to solve for X, I'm going to do a process called cross multiplying. What that means is I'm going to take my numerator of 30, and I'm going to multiply it across to the denominator. So I'm going to take 30 and multiply it by 15. By doing that, that's going to give me 450. I'm also going to do the same thing with x. I'm going to multiply it by 18. So cross multiplying, I'm going to multiply kind of like in an x. The numerator of one times the denominator of the other, and I'm going to multiply the other two. Now multiplying 18 times x would give me 18x. And it sets up a simple equation I'm going to solve then by dividing by 18 on both sides. I will get x equals 25. So I know that this unknown side is 25, okay? So again, what I did is I wrote a proportion to try and solve for this unknown. All right, so let's do the same thing in example B. So here I want to figure out, again, corresponding parts based on my statement, and then I'm going to fill in my numbers to write a proportion, okay? Our goal here is we're going to try and solve for P to S. So P to S would be this right here. Now in this one, if I look at my similarity statement, it says TPR is similar to XPZ. And I want you to notice that there is no S written in here. I have TPR, which is this triangle, compared to XPZ, which is that triangle. So this one we might have to visualize a little bit more. So I know right here that P to S is probably going to correspond with P to Y on my other triangle, okay? So again, I know that P to S is going to correspond to P to Y. So what I'm going to do is I'm going to write this right away as a ratio. I can visualize that P to S is smaller than Y to P. So when I write this, what I'm going to write is PY, we're going to compare to P to S. What I'm going to do then is I'm going to relate this to other sides of my triangle. So for example, I am given here in my similarity statement, let's say that I'm going to compare this to T and R and X and Z. So I'm going to compare it to the long side here versus the long side there. Now notice you are given 6 and 6 here, so adding those together would give me 12, and here 8 and 8 would give me 16. That's a terrible looking 6. Okay, so when I want to compare these two, I'm going to compare this to X to Z and T to R. Now filling in my numbers, it would look like this. I know that P to Y is going to be 20, and I'm going to compare that to P to S, which I'll label as X, okay? And then I'm going to compare that to XZ, which is 16, and its corresponding part would be 12. Okay, so I had to do some little bit of algebra here to figure out some of those unknown sides. But now that I want to solve this, what I'm going to do is solve this by proportion by cross multiplying. Okay, so I'm going to take 16 times x, which would give me 16x, 20 times 12, which will give me 240, and then lastly, I want to divide both sides by 16, which is going to give me then 15 for x. So I know that that unknown side, P to S, is going to be 15. So here I'm setting up a proportion in order to solve. Now just know that there are different ways I can set up a proportion. So the way that I showed it on here might have been different than maybe how you tried it, okay? So for example, I could have done 20 over x equals 8 over 6. Instead of adding those things together, I could have just recognized that this 8 corresponds to that 6, okay? Same thing, but different. Very similar, but not the exact same. See what I did there? All right, last two things we're going to do here is compare this idea of similarity and proportions to some properties of shapes called perimeter and area. So this is something you had to do on that simulation. So again, the perimeter is adding up all of the sides of any sort of polygon. So let's say that I have KLMN. If I want to find its perimeter, I'm going to add up all 4 of these lengths to figure out what its perimeter is. It is the distance all the way around. Same thing here, it's the distance all the way around. Okay? Now, when we look at and compare the perimeter of one polygon as compared to the other, what we're going to see is that the ratio of the perimeters is going to equal the ratio of the two sides. So for example, let's say that K to L was 10 and P to Q was 20. By looking at the ratio of those two sides, 20 divided by 10 would give me 2. Now that 2 means that this shape is going to be twice as big. So if I look at the perimeter, let's say that this perimeter was 100, that means that the perimeter of the second shape is going to be twice as big, so 200. So the ratio of the perimeters, I'll write P big compared to P small, perimeter P for perimeter, is going to equal the ratio of any two sides. So for example, here I did PQ to QL. So let's apply this to an example. So I have here gazebos, A and B. All right, now what I want to know is what is the perimeter of gazebo A? Now, if I want to find the perimeter of A, what I would need to do is add up all of my sides here. But guess what? I don't know any of the sides. All I know is this side 10, okay? But what I do know is that if I compare the perimeter of one to the other, that they should be the same ratio as the ratio of any two sides. So what I'm going to say here is I'm going to write the perimeter of B compared to the perimeter of A should equal the ratio of any two corresponding sides. And based upon this diagram, I see that AB corresponds to FG. So what I can say here is that the ratio of those two perimeters will equal the ratio of those two sides, FG to AB. So then to solve this, what I got to do is just plug in the values that I know. So real quick, I do know the side length. So I do know that FG is 15. I do know that A to B is 10. Okay. I do need to figure out the perimeter of B by adding up all these sides. So if I want to find the perimeter of B, I'll just write off to the side here. I'm going to take 15 plus 9 plus 12 plus 15 plus 18, add up all the sides, and that's going to give me 69 from a perimeter of B. So that is the perimeter there. And my goal is to find the perimeter of A, so I will label that as X. To solve that again, just like the other problems, I'm going to cross multiply. By doing so, I'd get 15 times X, which is 15X, 69 times 10, which would be 690. Then if I were to divide those two things out, I'm going to get X equals 46. So I know that the perimeter of A is going to be 46 meters. Now, same thing that was true about perimeters is also the same about the area. Now, the area is a little bit different because the area does not represent the distance around the outside, but it represents the space occupied by a shape. So you'll see the shaded region in blue, that's the area. Here, the shaded region in red, that represents the area, okay? So when comparing area, it's slightly different. Now, these two shapes are something that we probably don't know how to find the area of. But one simple shape we do is, let's say that I had a square. Square where all four sides are the same, and let's just say that these were 2 and 2. And let's compare that to a similar square, which is going to be bigger, and let's say that this square has sides that are all 4. So let's say 4 and 4 all the way around. So if I wanted to find the area of a square, what I'm going to do is just multiply the two sides together. So here if I did 2 times 2, that would give me 4. Here if I did 4 times 4, that would give me 16. Now comparing this, here's what I see. When I compare the corresponding sides, so let's say this side to that, I see that the side is twice as big. But when I compare the area, 4 times 2 does not give me 16. 4 times 2 would give me 8. So what we see here is that when we compare the ratio of the areas, so when I compare 16 divided by 4, and that gives me 4, that does not match up with our scale factor of 2. So what's the relationship that we got going on here? Well, the reason why we're getting two different answers is because of how we find the area of a shape. The area is found by multiplying two sides together. So 2 times 2, 4 times 4. Now what we know is that this square is twice as big as that one. So this side, the 4, is twice as big as that one. And it's also true that for this side, that one's twice as big. So when I multiply 2 times 2, each of these is being doubled. So my scale factor is being doubled. I shouldn't say doubled, but my scale factor is occurring twice. In math, anytime we're multiplying by the same thing more than once, in this case twice, that means that we're squaring it. So what ends up happening is that if I find the ratio of two sides, so if I look at the ratio of, let's say, 4 to 2, what I want to do is I'm going to take that ratio and I'm going to square it. Now, if you follow the math, 4 divided by 2 is 2, and if I square that, I'm going to get a scale factor of 4. Which means in terms of the area, even though we know that the scale factor is 2, if I look at this shape and compare it to the second one in terms of their areas, what I know is that the area of the second shape is going to be 4 times bigger. So even though the scale factor is 2, the area's scale factor is going to be square that value. So in order to find the scale factor for the areas, we're going to find the scale factor between the two sides. We're going to square it, and that's going to find the scale factor between the areas. So now let's apply that to an example. So I have here triangle ABC compared to DEF. You are given a set of corresponding sides, 10 to 5. And we're given the area of ABC, which is 36 square centimeters, and I want to find the area of DEF, which again I don't know. Okay, now kind of relating to what we just talked about, we know that obviously ABC is going to be bigger. So scale factor-wise, if I look at 5 to 10, this is an easy one to figure out, I know that the scale factor is twice as big. Now, where it gets confusing is that just because the lengths are twice as big, that does not tell us that the area is twice as big. To relate the area, it follows that square relationship that if I look at the ratio of the two sides, 10 to 5, by dividing them out, 10 divided by 5 would give me 2. But the area is a square ratio, which means I take 10 divided by 5 and square it. I'm going to take that scale factor of 2 and square it. So 2 squared would give me 4. What that means is that in terms of the area of triangle ABC is going to be 4 times bigger than the area of triangle DEF. Okay, so if I know this area, I know that that one is going to be 4 times bigger. Now to work backwards like we're doing, so here we're going from 36 trying to find that one, I'm just going to do the opposite relationship and divide it by 4. So 36 divided by 4 would give me 9. So I know that the area of that smaller shape is going to be 9 square centimeters. So it gets a little confusing with the area, but when we look at the area, it's going to be a square ratio, which is slightly different. So in this lesson, we looked at similar objects and tried to solve what is called proportion by looking at those corresponding parts. Guys, got any questions? Make sure you jot those down. Otherwise, good luck with the practice problems. We'll see you next time.